let's just finish the slide deck here with the examples that we were working on in today's lecture. So here, going forward from our previous discussion of the difference between strong induction and weak induction, you can see here, hopefully, that we now have a question where this recurrence relation relies on two previous iterations of the recurrence. What do I mean by that? I mean that in order to identify what T of n is, let's say this is T of n on our list here, we need to know what T of n minus 1 and what T of n minus 2 are, okay? So not only does it hold or is not sufficient to just know what T of n minus 1 was, we need to know both. Okay, so this should already be a big clue that we need to use strong form of induction in order to prove this. So we'll use, as always, our base case. This is going to be when n is equal to 0 or n equals 1, right? Those are our two basis cases that are given to us. Furthermore, we need to prove that both of them hold. Why? Because, again, since we're using strong induction and since the nature of the question relies on two previous examples, then we need to have at least two examples solved so that before we can move on to the third one. Okay? If we just prove at n equals 0, but we don't know what n equals 1 is, then we can't figure out what T of n equals 2 is unless we know both n equals 0 and n equals 1. Okay, so we need to prove those as our base cases. So n equals 0, we will have, this will be the definition here will be the left-hand side, and this will be our right-hand side. So left-hand side, T of 0 is equal to 1. Right-hand side, we have 2 to the 0, which is equal to 1. Now, is 1 less than or equal to 1? Yes, it is. So this holds for our case, n equal to 1. Now, n equals 0. Now, n equal to 1, we have T of 1 equal to 1. We have 2 to the 1 equal to 2. Is 1 less than or equal to 2? Yes, it is. So it holds when n is equal to 1. Now we'll move on to induction hypothesis. And again, we need to use the strong form of the induction hypothesis here. So we will assume that T of L is less than or equal to 2 to the L for all values of 0, less than L, up to some number I, which is less than n. Again, I might call this I, you might call this K. It's really whatever variable name you want to put there. The main point is it's not all numbers, right? It's not, we're assuming that this holds even for n inclusive. It's just holding for some set of values up until L. And we need to prove that it holds for L plus 1. So that's going to be our induction step. We want to show that T of L plus 1 is going to be less than 2 to the L plus 1. So we'll start with T of L plus 1. T of L plus 1 is going to be T of L plus T of L minus 1. That's coming directly from the definition right here. Now, we have, because of strong induction, we know that at L and L minus 1, our claim holds, right? It's within that grouping that we're allowed. So we know that this must be less than or equal to 2 to the L plus 2 to the L minus 1. Okay, by our induction hypothesis. Now, this is less than if we just increase this L minus 1 to a power of L, which can help us, right? 2 to the L plus 2 to the L. This is going to be more than this previous sum because we have increased the exponent. And then this is great because now we can merge these two terms into just T of L plus 1, which is exactly what we are looking for. So we have shown that T of L plus 1 here is in fact less than or equal to T to the L plus 1, following this set of logical equalities or inequalities. Okay, we can conclude with our conclusion, which is just going to be, therefore, by induction, T of n is less than or equal to 2 to the n for all n greater than or equal to 0. Okay, so moving on into bigs and littles. Hopefully you are becoming much more comfortable and confident between using these big O, big omega, big theta, little o, and little omega notations, and also comfortable using the limits in order to prove if f of n is some big O, little o, etc. of some g of n. Let's take a look at this example, which is definitely a bit more tricky though, just to make sure we're all on the same page. So we want to show that log p of n is big O of log n. And we have that p of n is some polynomial in n, and where our constants are greater than 0. And we have that k is at least 1. So because we're dealing with log p of n, we need to first start with log p of n. And remember, the definition for big O is showing that f of n is less than or equal to some constant times g of n for all n greater than or equal to some n naught. Okay, so we need to find values c and n naught such that this is true. Again, this is going to be our f of n. Log p of n is our f of n, and log n is going to be our g of n. So in particular, we want to show that this log p of n is less than or equal to some constant times log n for some values n greater than, for some value, all values n greater than or equal to n naught. Okay, so this is what we want to show. So we'll start with log p of n. And log p of n is going to be the log applied to this polynomial. So it's going to be log of ck and k plus ck minus 1 and k minus 1 all the way down to c1n plus c0. Okay. Now this is going to be less than or equal to the log of all of these to the power of n to the k. So we would just replace all of these n to the k, n to the k minus 1, n to the 1, n to the 0 with n to the k. So c n k plus c k minus 1 n k plus dot 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 plus c1 n k plus c0 n k. Okay, so now that this is all written in terms nk, we can factor out that nk. So it's going to be log of ck plus ck minus 1 plus dot 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 plus c1 plus c0, all of that multiplied by nk. Now we know from our log rules that if we have log of x times y, this is actually equal to log times x plus log y. So now that we have these two terms separated out, we can do the same thing here. So this is going to be equal to log of just the constants, c1 plus c0, plus the log of just n to the k. And furthermore, we should have our logarithm rule, that log of x to the y is equal to y log x. So we can further simplify this term here to just be k log n. So we get this term here. Now, we need our term to be in the term, or we want our answer to be in the form c times log n, right? We want this here. And we're almost there. We have k times log n, which is great, but then we have this plus constant on the side, which is not as great. So how can we maneuver this to make it all just one constant times log n? Well, we can multiply this side by log n, okay? So this is going to be less than or equal to log ck plus 1, or ck minus 1, plus dot 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 plus c1 plus c0 multiplied by log n plus k log n. And now we can factor out our terms of log n, and it will be log of our constants plus that k over here, all multiplied by log n. Okay, so this is great. This means that this here, and notice that this is only constants, right? Log of any sum of constants is still just going to be a constant. And our k is also some constant, some natural number that's greater than or equal to 1. So let's add a page here. So we will have we make some space here. That's our value for c is going to be log ck plus ck minus 1, etc., all the way to c0 plus k. And we just need to see when this inequality is going to hold that we have up here. Okay, so we have an inequality here, and we have an inequality here. And when do these two inequalities hold? Well, this one is going to hold as long as n to the k is greater than 0. So as long as n is greater than 0, we will have that this inequality holds. This inequality holds as well, I believe, at n greater than 0, but I think this one holds at n greater than or equal to 1. Because then we have something multiplied by 1 multiple times, it's not going to get any smaller. And if it's anything bigger than 1, then it will just simply get bigger. So this inequality holds at n equal to greater than or equal to 1. This inequality here as well holds at n greater than or equal to 1, I believe. But I think it's safer to say n greater than or equal to 2. Again, we will assume all of our logs here are base 2. So log base 2 of 2 is 1. And that way we can just ensure that log base 2 of n is always going to remain higher than or equal to 1. So we'll take the max of these two values for our n, and that will become our n naught. So n naught greater than or equal to 2 is certainly going to be an acceptable value here. And there we have solved the question. We can conclude, therefore, log p of n is in fact O log n.